and welcome to our channel. My name is Daria and I'm a part of the Exactpro research team. At Exactpro, we build software to test software. Do check out our website exactpro.com if you want to learn more about us. You can also subscribe to this channel and hit the bell button to make sure you see all the new episodes as soon as they come out. In the previous video, we started reviewing Chapter 1 of A4Q's AI and Software Testing certification. We talked about AI history and reconstructed a timeline containing all the key dates. We also talked about the Turing test, which is a way to assess the work of a chatbot and its underlying algo. If that's the information you're looking for, go ahead and watch our previous episode. Last time, we mentioned the terms symbolic and subsymbolic AI quite a lot, so let's finally define what these are. Symbolic AI implies formalizing reasoning through mathematical logic and automatic deduction techniques. Compared to subsymbolic AI, the reasoning and its results can be explained and their validity demonstrated. All object-oriented programs can be considered symbolic AI. Let's review an example. In one of its simplest implementations, symbolic AI is a software library that analyzes a mathematical formula entered by a user to figure out the correct order of operations. Formal verification of algorithms is yet another area of symbolic AI. However, that's not what most people think about when they think of AI and ML, which brings us to subsymbolic AI. The technology supporting subsymbolic AI has a lot of household names under its umbrella. This is the type of AI that doesn't deal with formal notions and only deals with data. The best way to describe it is by saying that it identifies what can be found in or learned from the existing data to make decisions about unknown situations. Machine learning is the main domain of subsymbolic AI. It's also the domain that the rest of the syllabus will be focused on. It relies heavily on statistical techniques to represent data and reason on it using different types of learning. In the field of machine learning, techniques, algorithms, and models are three different but related terms. Techniques refer to mathematical representations and methods adapted to machine learning. Algorithms define how these representations are treated, and finally, the notion of a model refers to an algorithm trained with training data. The four major types of machine learning are supervised, unsupervised, semi-supervised, and reinforcement learning. Supervised learning can be applied to a multitude of tasks. The key here is to prepare labeled data to train the algorithm. This means labeling the input and output and having the model establish the dependencies or the relationships between them. In image recognition, for instance, data scientists take a set of pictures of, let's say, hedgehogs and fish and mark them with corresponding labels. After that, the program can define, with a certain degree of probability, which of the animals is in the picture. Unsupervised learning differs in that it doesn't need labeling. Unsupervised learning algos are able to imitate human reasoning and find their own dependencies without being prompted by pre-marked input and output. For instance, the example mentioned above will now look like this. We won't label the images, but let the algorithm split them into groups or clusters using its own logic. Another example is a large stream of data that can be loaded into the system to check it for data anomalies by trying to break the stream of data into several clusters. The clusters themselves, as well as the values that stand out, also known as outliers, would be interesting to look at and can be further manipulated depending on the goals. This way, we get some information about the data without having to train the system. There's also semi-supervised learning. It combines both supervised and unsupervised learning by using a set of labeled and unlabeled data. This technique reduces the amount of labeled data required for training. Last but not least, reinforcement learning. This is when we continuously compare the model against itself and against other models and gradually improve it. One of the most famous examples here is DeepMind's AlphaGo Zero. Another example is the neural nets generating realistic people's faces out of a pool of available real-life images. This is implemented in a project called This Person Doesn't Exist. The algorithm that underpins it is called Generative Adversarial Network. This neural network has endless creative applications, including those in robotics, design, and so on. To pass the exam, it's important to understand how these four types of subsymbolic AI differ and what techniques they operate with. Here you can see the main techniques mentioned in the syllabus. To become more confident in these differences, you may have to go beyond the syllabus. A standard beginner machine learning course would reinforce your knowledge of the basic concepts. Moving on, the exam is also bound to contain a question about the naive Bayes classifier. If you choose to explore it further, we suggest going through a lecture we will link for you in the description box. It would be a great source of information on the topic. As we've discussed, ML and AI assessment is still an outstanding issue. The section concludes with the list of accepted machine learning metrics. These are accuracy, true positives, true negatives, false positives or type 1 error, and false negatives or type 2 error. We'll talk about them in more detail in Chapter 2. The next section looks into the principles of work of 5 ML algos. The list includes Bayesian belief networks, naive Bayes classifier, as well as support vector machines and k-means. This is accompanied by a throwback to the perceptron learning algorithm. Moving on to the next section. It starts with highlighting the importance of the quality of data in AI. Even the most accurately chosen algorithms won't perform well on little or low-quality data. This is why ML scientists spend a large part of their time collecting, cleaning, exploring, and reorganizing their data. As for the software development techniques in ML, the syllabus limits this section to the content of one article describing CRISP-DM. This stands for Cross-Industry Process Model for Data Mining. The concept behind the model is quite intuitive. It consists of several steps: business understanding, data preparation, modeling, and deployment. However, the mock exam questions for this chapter are more focused on the definitions of terms than the concept itself. Another important part of the exam and the syllabus is dedicated to the notion of bias and cognitive bias in AI. This chapter merely introduces the issue, which in fact relates directly to the quality of the initial data. Extra information on biases is widely available online, and the syllabus will also circulate back to it later in the book. The example we wanted to share with you here is a recent solution called Face Depixelizer. The tool has recently become an embodiment of algorithmic bias. It's supposed to reconstruct sharp images of people's faces from a heavily pixelated, low-resolution image. One point to understand here is that it's not reconstructing the original image per se, it's the algorithms trying to retrieve the missing pieces from similar data available and match them to the image. Right away, it became evident that the tool is inclined to reconstruct the faces of people of ethnic backgrounds to look white. This is a result of dataset imbalance. In other words, the model had predominantly been fed images featuring people of the Caucasian race and few or no images of people of other origin. So from that dataset, it inherited the Europoid proportions and genotype characteristics and is basically unable to create an image that looks different. So when a model gets bias in, it gives bias out. There also have been unfortunate cases of algorithmic bias in mortgage lending, healthcare, and many other industries. There are few videos dedicated to A4Q's AI and software testing certification. One of them was recorded by Rex Black, the author of one of the core books on the foundation level exam preparation. In this video, he walks us through the syllabus and mostly concentrates on what bias is, since at the exam, the probability of getting the question related to biases is extremely high. The last thing the chapter focuses on is the ethics issues around AI. In our introductory video, we mentioned that Exactpro has been part of the initiative to transfer the A4Q exam into the realm of the global ISTQB board. A lot of preparatory work is being carried out to improve the training materials and the exam itself. But the work has been hindered for the following reason. Currently, the syllabus covers the ethics issues around AI, while certain governments officially oppose the idea of it being a legitimate issue. On the other hand, the majority of countries believe that ethics issues are essential for the success of AI and they have to be included in the textbooks. So far, these parties cannot find a consensus. The following ethics issues should be considered as per the syllabus: explicability and accountability, fairness and non-discrimination, respect for democracy, justice and the rule of law, transparency, responsibility, reinforcement of existing bias, and consistency. The consideration of ethical issues is essential for building trustworthy AI. This concludes today's video. Thank you for staying with us through Chapter 1 of A4Q's AI and Software Testing Certification Review. In the next video, we will concentrate on the mock exam questions for Chapter 1 before we can proceed to the next chapter. We do have a lot more content for you. Feel free to look around, give us a thumbs up if you liked the video, subscribe to the Exactpro channel, and hit the bell button to be notified as soon as the next video comes out. I'll see you soon!